Yeah, so you see like kind of like a yeah, that kind of collapsed into this one. The sound is not exactly the same thing, but it kind of like merged into what we're doing again. Yeah, I mean, I have this thing with, I don't know, nobody doesn't have the same. Also, speaking about that, so yeah, that's interesting, I think. I mean, we're kind of stuck in the sense that we put a lot of thought and we made progress, but I think we need like something external to get like beyond the places where we're stuck. I mean, we have some results and things that has to be like better results. But yeah, the biggest, yeah, I mean, it's not that easy.
Zero.
Or zero at the beginning.
Będzie układów o 14:30 będzie jeden dodatkowy klub. Wszystko damy znać. Super.
You're back?
One more minute, so
told him we stay here.
Yeah.
I told him a few days ago the bed is actually very bad.
Okay, I should start.
But I forgot what I tested. I guess you only need to test
So,
once.
what I'm back, and the last talk in this morning session will be given by Dominik Kwietniak, Jagiellonian University. After Dominik will talk to us right in rigidity versus flexibility, Choquet simplices, all that.
Great. Thank you very much. It's a big pleasure to be here. And behind every organizational committee who here did a lot of work, there's also one mastermind. And Artem is here, the mastermind of all this event. So a special thanks to him. Now, what I'm going to tell you about is a joint work with a group of people, those are Sejal Babel, Jiernei Cinch, Till Hauser, and Piotr Procha. And the rigidity versus flexibility is our motivation. So the late Anatol Katok, he liked to pose a little bit more structural questions about dynamical systems. So he proposed a program, which is kind of a meta program to study phenomena he called rigidity and flexibility. So what are those? It is like that we study dynamical systems. So maybe I should say here group actions. We study group actions. Maybe this will be closer to your hearts. And those group actions, they have many properties. And among those we have families of group actions. And we ask about the following questions. Which of the properties can be realized inside a given family of group actions? Okay, say we have an invariant like entropy, and we have a family of dynamical systems or group actions, and we ask what values of entropy can be realized inside that family. And flexibility is a phenomenon which appears in many families of dynamical systems, in which that in the sense that a family is flexible is only trivial restrictions are real restrictions. Otherwise, we see realization of all possibilities for a given set of invariants. And the rigidity is a control, is a kind of the other part of the spectrum, in which the given invariants can be realized in only very rigid and specific way, but in general we a priori have more possibilities. So a natural question about that is a question: what is a generalized shape for a simplex of invariant measures? So in my setting, I can stay with the compact metric space, and I take an action of a continuous, a homeomorphism, a z action. I study this situation, and then I take the set of, in this setting, the set of all t invariant Borel probability measures is always non-empty, and the set of, and this is a compact, we end it with the Weak star topology, so it becomes a compact metrizable convex subset of some locally convex topological vector space. And it turns out that ergodic measures, so in some sense, in the composable component, in the composable invariant measures, are the extreme points of this simplex. So, and then there is ergodic decomposition theorem. So by a theorem called ergodic decomposition. By the way, can you read that? Nicanor, can you read what is written? Okay. So by ergodic decomposition theorem, it turns out that this set of invariant measures, this convex compact metrizable set, is an object known as a Choquet simplex. So in finite dimension, we all know that among all convex compact subsets of finite dimensional vector space, we have a special family of convex subsets which are the usual simplices. So zero-dimensional simplex is just the point, one-dimensional simplex is just a line, two-dimensional simplex is just a triangle, and and in each dimension we have exactly one simplex. What is special about those simplices among all compact convex invariant sets? What is special about them? Well, it is the uniqueness of the representation of any point inside that simplex as the affine combination of the extreme points. So a disk is also a compact convex subset of RD, but non-extreme points can be described as a convex combination of extreme points in many different ways. In simplices, the representation is unique. And now what are the affine coordinates for a point in the triangle? It is the nicest part is to say, well, I can distribute a unit mass over the three vertices of the unit triangle, and I can distribute, and this distribution of the unit mass determines me a single point which is the center of gravity. This is a point at which if I support my triangle, it will be balanced. So I really distribute a unit mass among the vertices, and each such distribution represents a unique point inside the triangle. Now, Choquet simplices are just a generalization of this notion for possibly infinite dimensional spaces. This time we do not distribute a discretely unit mass, but now we are allowed to distribute a probability measure over the set of extreme points, and a similar formula gives us the unique decomposition of a given. So each point is represented by a unique Borel probability measure living on the set of extreme points, and this is what distinguishes all Choquet simplices or just compact metrizable convex subsets of this. So this is a well-studied family. So we know that every set of invariant measures is an example of a Choquet simplex. But then, of course, there's not natural question: how flexible is that? Is it true that every Choquet simplex is affinely homeomorphic to some set of invariant measures for some homeomorphism acting on the compact space? And the answer is yes. This is a theorem by Dominik from early 90s, I think 92. And he proved the following, that every Choquet simplex. K is a finely homeomorphic, so there's a homeomorphism which is also an affine map to MTX for xt being a minimal subshift. So for the family of homeomorphisms of a compact counter set, we already have an example of flexibility. It is known. Now, there is no flexibility, say, for homeomorphism of the unit circle. Every homeomorphism of the, I think, okay, let's say every C2 diffeomorphism of the unit circle is actually rigid. It has to be conjugated to rotation, and therefore there are only two, and if the rotation number is irrational, then it is uniquely ergodic, so there is only one invariant measure. So no chance for any kind of result like that. For the compact interval, we cannot have minimal homeomorphisms at all, but one can ask, okay, how about transitive actions, transitive transformations? But then it turns out that for any transitive transformation, there is only one possible shape of the set of invariant measures, which is so-called Paulsen simplex. This is a unique phenomenal object in which all the extreme points are dense. So it is hard to imagine how extreme points of a compact convex sets are dense inside the set, but there is, okay, except the singleton. So for other examples, there is a unique up to affine homeomorphism example of such a guy. This is Paulsen simplex, and it has many interesting properties, but it is the only possible shape for transitive maps, for the simplex of invariant measure of the transitive map on the interval. So okay. So now, what is the next question? How about other groups? And about other groups, here, Maria Isabel Cortez and her collaborators, they have a very nice results generalizing Dovnarovich result for minimal actions of amenable residually finite and amenable monotiable groups. So the same theorem holds here. But how about manifolds? How about if I ask you about what are the possible shapes of the simplex of invariant measures for a minimal homeomorphism of acting on a manifold? Yes?
May I ask you a quick question about the Paulsen simplex? Is there some natural class of minimal subshifts that realize that?
So nice, no, in the sense that it is for minimals. So in general, for minimal subshifts, it is not easy to get non-trivial number of ergodic invariant measures, because low complexity measured by exactly complexity forces the set of gives some bounds on the number of even ergodic invariant measure a system may exhibit. So actually, I think that at first, in the 50s and 60s of the last century, actually they were surprised when Hahn and Perry they came up with the first examples of a non-uniquely ergodic minimal homeomorphisms, because it was even believed that minimality should force those guys to have only one invariant measures. So later there was like a sequence of works showing more and more possible ergodic invariant measures which precede Dovnarovich result. So in particular, Susan Williams was the first who proved that there are uncountably many different ergodic invariant measures possible. But Dovnarovich result is ultimate in the sense that it resolved the problem completely. So it's not. There are some examples. They are possible to get, but it doesn't seem to be like a nice class in which this is not natural. I don't think it's
Constructive?
Well, I can give you a construction of an intersection of Sophic shifts which give you a shift with the Paulsen simplex as the set of invariant measures. So in this sense, yes, it is like there are recursive formulas how those Sophic shifts should behave, and I think a similar proof procedure can be used to prove that the ergodic measures are dense also for other examples appearing in the literature. Because in a sense, a trick is that every subshift has a sequence of a finite shifts of finite type approximating it. So every subshift is always an intersection of shifts of finite type. And taking intersection is also the same as taking convergence in the Hausdorff metric on the space of subshifts. But there is another metric coming from Ornstein. It's a pseudometric on the space of subshifts coming from Ornstein theory of Bernoulli shifts, which measures the distance not in the usual topology, but measuring the density of the positions at which two sequences differ, the bar pseudometric. And if your subshift is chain mixing, it's a technical condition saying that all the shifts of finite type approximating it, they are mixing shifts of finite type, and the approximation is good not only in the usual topology, but also in this pseudometric given by the D bar, then the density of invariant measures is inherited by the intersection. So now the whole construction of a subshift, okay, the proof, the proof not applying Dovnarovich theorem, but like a direct construction of a minimal subshift with a Paulsen simplex of invariant measures is to carefully pick a sequence of Sophic shifts which are getting closer and closer to minimality in the sense of synthetic return times, and making sure that in D bar they also are getting closer and closer, and then applying this general theorem, and you have it. So yeah. So this is one thing, and okay. So there is a theorem with a, I think, deeply non-trivial proof by Foreman. So this theorem is actually a corollary of a Foreman and Weiss construction, and let me state it. The same for minimal, non-minimal, for diffeomorphism. So Foreman and Weiss, when they were going after some anti-classification results for ergodic measure preserving systems, they produced a very abstract method of translating examples from Cantor systems, like from Dovnarovich work, into examples of diffeomorphism of smooth diffeomorphism of T2. I think it's a long paper with a very complicated construction. How you can translate the construction over the odometer, which is the base of a construction here, into a construction over irrational rotation. But I discuss with both of them, and the examples are not minimal. it's kind of inherited in the construction that they are not minimal. Maybe this can be changed, but not easy. Apparently, without rewriting a huge part of the paper, which is again not easy. So we use a little bit different things, and we have the following. So this is 26, I hope, plus. So the first version of proof is actually available in the Sejal Bubbles PhD thesis, which is written and submitted for that. So we are just preparing a preprint with the whole introduction and all contributions for other co-authors as well. So if M is a manifold satisfying, I will give you the condition in a moment, some assumptions. Then for every K Choquet simplex, there exists minimal homeomorphism G from the manifold to itself with the simplex of invariant measures of G on the manifold being affinely homeomorphic with K. So we are able to produce such an example for a class of manifolds. And what is the class of manifolds? Star is dimension of the manifold is at least 2, and there exists F, capital F from M to M, minimal uniquely ergodic homeomorphism. So what is uniquely ergodic? Homeomorphism is the homeomorphism which possesses only one invariant measure. So for example, the irrational, if we take an irrational flow on the torus and we take time 1 map, then that will do the trick. So if it is known that there are a lot of manifolds which have this uniquely ergodic, which carry those uniquely ergodic homeomorphisms. And then we cheat, because instead of using like 100 long pages of Horman and Weiss, we use some 50 long pages paper of some other authors, which provide us a very useful tool. This very useful tool is a theorem by Banach, Crovisier, and who's the third author? I'm sorry.
These are compact manifolds, right?
Yeah, compact, of course. Yeah, compact manifold without boundary. Banach, Crovisier, Leroux. I think it's Leroux. So they vastly generalized the Danjois-Ries technique. So the first examples of an interesting homeomorphism on manifolds were provided by Danjois, who modified irrational rotations to show that non-minimal examples are possible, and he did it by some kind of a surgery. It is like you take your irrational rotation and you change what is happening over one orbit. And then, in fact, Marie-Ries, she produced some zero entropy minimal homeomorphism of the two torus, and she used a very similar technique. And those three gentlemen they took the very similar idea and they went much farther with that. So they have a more general theorem, but the version of the theorem which we are interested in is the following: if M is a manifold satisfying the same assumption star, and H is a homeomorphism of a counter set which is minimal, then there exists G from M to M such that we can state it like this, that the set, the simplex of invariant measures is a finely homeomorphic with the simplex of invariant measures of the product action of A times G on the manifold times C. Okay, I will finish stating a theorem and I will tell you how you should read it. So here is a statement, and what it means. It means that you start with a manifold, you have your minimal homeomorphism which carries a unique invariant measure, which means that in a sense the statistics of return times of any point to any neighborhood are very regular. They converge nicely, and then you take somewhere there you take an abstract counter set homeomorphism, and you form a product system. So you multiply your manifold times this counter set homeomorphism, and you take the product action. This is impossible to make this system, to copy this system completely back onto your manifold, but you can, blowing up over some orbits, inserting them there instead of single points, counter sets which are moved. You may try, which are being moved like F asks. You may mimic enough of the dynamics of H on those fibers which are now collapsed onto the manifold, so that you will see a so-called Borel star conjugacy, which in particular gives you this.
This F?
G, right?
It's
The F should be G?
no, here F. F is this one. It's this original one. Okay?
And it should be always uniquely ergodic.
F is always, for the theorem to work, it's uniquely ergodic, and actually this helps us enormously, as you will see in a minute. So, well, now.
So in particular, this suggests that even if F is a diffeomorphism, then there's probably little chance that you get G.
Yeah, no, of course. Even if, and in many cases, F is a diffeomorphism, but you destroy it very badly locally in a way that no, that there is no hope. I think not with those methods. Although okay, they are very hard to understand, at least for me. Hermann examples of a T4 diffeomorphism with uniquely ergodic with zero entropy, or with I think with zero entropy. Okay, they are, yeah. So now, if we have, you know, I think in every part of mathematics we have formulas which are equivalent to a school children dream formula for adding fractions, right? For me, what would be here the super nice formula if I could do this. That would be, and then if this formula would hold, then basically we should just substitute Dovnarovich examples here and we are done. Unfortunately, no. Unfortunately, this formula is in general not true. the point is that the simplest example is you take irrational rotation and you take a Cartesian product with the same irrational rotation. So you have two systems which have only one ergodic invariant measure, but the product system has plenty of ergodic invariant measures because now on the diagonal leaves a copy of the irrational rotation. On the graph of every power of irrational rotation leaves another invariant measure, which is a copy of irrational rotation. So there are many invariant measures, and this formula, the point times point, doesn't hold. Yes?
Just the G that David, is it minimal or?
It should be, yeah, here I assume that it is minimal.
But is G minimal? But the G...
Yes, G is minimal, and this holds. They also have some they have more general theorem about translating transitivity and other properties, but this is true for sure, and I'm not sure that if this is important, that H is minimal. Maybe not. That this is for many reasons not important, because in some sense on the counter set getting minimality is not that super hard. So this is unfortunately not true, but it is true under some additional conditions. So Furstenberg notions of disjointness comes to the rescue here. So if I take two compact dynamical systems, so assume that the first measure is mu and belongs to the set of invariant measures of the system MTX, and nu is an invariant measure given by the system Y, by the action of S on Y. So mu is disjoint with nu if the product measure mu times nu is the only measure the only measure which is T times S invariant and projecting to mu and nu respectively. Right? So I take two invariant measures. I take the product system. So of course for the product system, the product of my invariant measures is invariant. And this product of invariant measure has this property that if I take projections on marginal projections on each coordinate, I recover the original measures. But as we discussed for the example for the irrational rotations, this is not always the unique invariant measure. For the irrational two copies of the same irrational rotations, we see many measures which have the property of being projected onto those coordinates. But if there's only one, if the obvious one is the only one, then we say that those two measures are disjoint, and we use this notation, and now here we have an important condition. So now let me assume the following. Assume that for every nu which is an invariant measure on my counter set minimal homeomorphism, so MHC, nu is disjoint with a measure mu, which is this unique invariant measure of capital F. So the assumption is that capital F is uniquely ergodic, so it has only one invariant measure, so let's denote it by mu. So now assume that we are coming into that theorem, into the Beguin-Crovissier-Leroux theorem with this counter set homeomorphism, which in addition satisfies this. Then what is happening? What is happening? If you look carefully into that formula, then we see that the actual candidates for the ergodic invariant measures of this product system are now just mu times nu, when nu is just an ergodic invariant measure of this. And the candidates for the ergodic decompositions are also obvious. So this formula holds. So we are good. So if only we can find this, then so now Dovnarovich result applies can be applied directly to this, but a priori you would say, well, it is not that super. So systems in Dovnarovich examples, they always have a rational eigenvalue. So what if you start with something here which has a rational all rational numbers as eigenvalues? You cannot guarantee this. Okay. So a question which is interesting in itself, and it was also not only of completely impractical value, because the same problem that was faced by Forman and Weiss. They also had to retranslate everything from rational to base all the construction over one single irrational. So now we reduce the question to the question about the existence of those counter system with a given simplex of invariant measures and this property. And this is a question we like because we could solve it. You know, it's like with songs you like because you've heard them earlier and all this stuff. So we were able to construct such a family of examples, and this gives the theorem. So now I think I have like 14 minutes, and I can let you go for lunch earlier, or I can torture you with some ideas for the proof. So because it is not nice to organizers to finish 15 minutes ahead of time, I will try to finish maybe a little bit earlier. And anybody who is hungry, you can. I'm not interested. It's okay. So, guys, now ideas of proof. So, ideas of proof, they give us hope to generalize this method much farther. But now the idea of proof is the following. We have this uniquely ergodic homeomorphism. And now a nice thing is that this unique invariant measure of this uniquely ergodic homeomorphism has only countably many eigenvalues. And we have uncountably many irrational numbers. So we can pick an irrational eigenvalue, an irrational number, alpha, which is not in the spectrum of my invariant measure mu. Which means that now I can base the whole construction of my homeomorphism using irrational rotation over alpha as a kind of a base for the whole construction. That's here the nice thing of going into irrational numbers. And by the way, this gives you a chance also to use all the techniques like approximation by conjugation, by Katok and stepping to try to produce the homeomorphism. So this is the first step. The next step is the following. It is like a symbolic dynamical system corresponding to an irrational rotation is so-called Sturmian system. So how we should imagine a Sturmian system we think of the circle as the unit interval with the endpoints identified, and we have our irrational number. And for example, we take the interval of length alpha here, and we take a function which is the characteristic function of the complement. Maybe not alpha, we can take, say, gamma, which does not belong to the orbit of zero under the rotation by alpha, and we take this function with two values, and then we take the orbit of zero, and we start rotating this orbit of zero by alpha, and we start reading off a sequence of zeros and ones accordingly whether we end up in the interval here or not. In this way, we encode single orbit of the irrational rotation by alpha as a sequence of zeros and ones, and taking the closure of such an encoding with respect to the usual topology on the space of sequences endowed with the shift action, we obtain the so-called generalized Sturmian system. Okay? And now the trick is the following, that I can actually consider more general codings in which I take the partition of this interval into left closed half open subintervals, and I put values zeros and ones over consecutive intervals, like first interval is 0, then 1, then 0, then 1. So for example, I can take so this will look like something like this, but with infinitely many copies, right? And then I can repeat the trick, and this gives me a symbolic coding now using three symbols, 0, 1, and 2. This 2 is kept as a marker for the purposes, especially in the construction. But this gives me a family, infinite family of sequences. The closure of each sequence is now a minimal, uniquely ergodic, almost one-to-one. Sorry for using bad words, but almost one-to-one extension of the irrational rotation we started with. Okay.
Can you explain again what are these points? These are the orbits of zero?
No. I encode. So I take a circle, and I pick a function over a circle which corresponds to the partition of the circle into left closed half, right open intervals. And having this function over the circle, I take the orbit of 0, and I start moving, and I use my function to give this orbit a coding. And then I take the orbit closure of this coding, which gives me now the minimal almost one-to-one extension, because that's a function which has only countably many discontinuities, which means that the set of discontinuities is of higher measure 0, which means that this is almost one-to-one. That's a standard construction. But
excuse me, I wonder, does it make sense to continue to consider continuous function instead of piecewise constant?
So you won't get a continuous function into a finite set because the circle is connected.
Not really finite.
But if you take continuous function that you are recovering, I think that this almost one-to-one construction gives you a system which is isomorphic with the original one. And you won't get a symbolic system.
I see, okay.
And in a moment, the point is now that observe the following, that if I take, there is a nice thing about those simplices. Those Choquet simplices are divided into, they have a huge subfamily. So MTX is Bauer simplex, is a Bauer simplex, if the set of ergodic measures inside that simplex is a closed subset. So all finite dimensional simplices are Bauer simplices, and now it is known that for Bauer simplices, the topology of the set of the extreme points determines the whole simplex up to affine homeomorphism. So this is a nice generalization of the fact that the number of extreme points for finite dimensional simplex determines the finite dimensional simplex. So now imagine the following, that because now I can take a Bauer simplex, and this is a compact metric space. So I can embed it into a Hilbert cube. So Hilbert cube is a set of all 0-1 sequences, right? So any compact metric space is now embedded into this, and I can do the following, that any family of these 0-1 sequences, if I am clever enough, I don't want to go to this is not super clever, this is relatively simple. I just fix one partition and deciding over one element of partition how long I should continue the length of the symbol 1, I just look into the sequence of zeros and ones for my Hilbert cube, and I take a subinterval which is proportional of this length. So in this way I can faithfully encode all the sequences into those functions, and encoding into those functions I get an encoding into a family of unique invariant measures, and because this is all continuous, then I will get actually a set of invariant measures which is homeomorphic with my set. So then this is not possible to tell you about how you turn this family of measures into a subshift, but now this is a kind of a reverse engineering. You have your family of invariant measures given by a family of minimal subsystems which are pairwise disjoint, but you know that the shape of this family is the subset of ergodic invariant measures, which is your Bauer simplex, and you kind of do a reverse engineering to recover a single system which will be minimal and which will have this simplex of invariant measures. And the final step is to use so-called, well, not so-called, but theorem due to Edwards. And Edwards had this theorem in which he proved that an arbitrary Choquet simplex is an intersection of a countable family, descending countable family of Bauer simplices. So if you now play with those functions to encode Bauer simplices, then you can play with this theorem to encode a subshift in which the set of ergodic invariant measures will be like that. And the last condition, which is so those ingredients are now mimicking Dovnarovich proof in a little bit different language, but the ideas are the same. The final step, though, is not present in the Dovnarovich, namely, you need to check that all this construction preserved the disjointness you had, but luckily to us you can do it, and that's it. And of course the next step is to check whether an entropy function can be translated. And we hope we can do it, but we are not there yet. So thank you very much for your attention.
Thank you very much. Any comments, questions, suggestions?
So in your main theorem you get that there exists a minimal homomorphism.
Yes.
Can you get something a little better, some smoothness of this homomorphism, of this map?
Right now, not. Right now, once we use this as a black box theorem, I don't see it. It's like their constructions are of Alistair Windsor, a student of Katok, who produced use like I think minimal homeomorphisms with uncountably many ergodic invariant measures, but I don't think there is any clue how to get the shape. So right now, of course, smoothness would be nice, but most probably you would need completely different techniques than here. But still, starting with the irrational rotation, either from that or that theorem is a good starting point, and we would like to check what happens, but we don't know yet.
So where are they using the fact that this is a manifold?
They use this fact. So I think that they are after manifolds in the first place, and what is important to them is that there are some nice decomposition theorems telling that if you have like a upper semi-continuous decomposition when you have cells of the counter set and you collapse, then you still have something homeomorphic with your manifold. I think that this stuff is somewhere there, that it cannot be that like a completely, yeah, but like in the Dangerois example, you cut and you glue in an interval and you glue everything together, but you still have a circle. So this is a kind of thing that you still need to apply those theorems, and for manifolds there are a lot of this surgery results, I think, available. That's the truth. I don't know.
Maybe can you just comment? Maybe you already responded at some point. So what's known for dimension 1, like when you have a circle?
No flexibility. So
you don't get everything.
No. I think you get that either there are countably many periodic measures, which are like this is the Bauer simplex with the unit with the circle as the set of ergodic invariant measures, or just one. And I think that those are all possibilities.
Is there any way to run your method if you have a different f which is not uniquely ergodic? And start from there, like, you know, if you have some given Bauer simplex or...
I have, in fact, I have no idea, because we just, of course, this disjointness you can still try to if you have a good Bauer simplex, then yes, but say that the whole disjointness thinks, if you happen to have Bauer simplex in which you have a representative with any irrational number as an eigenvalue, then this breaks completely and you lose control of what you do after the product. If you have a Bauer simplex in which you know something, then this disjointness part, of course, is trivially true, and then you may think how this influences deconstruction. But again, deconstruction is really based on the fact that, okay, that they don't have to worry about many things you will have to worry about if you have non-uniquely ergodic system, because in uniquely ergodic system the return times uniformly converge to the measures, so everything does not depend on the choice of the initial point, and here you will have points generic for a specific measure, point generic for no measure, so this will get messy.
Yeah, I got lost in some parts of. Okay, so you take K, the simplex that you want to realize. You take alpha.
Alpha is directed by the invariant measure.
But then what you do is to construct a minimal, almost one-to-one extension of the rotation.
Of the rotation with K as a simplex of invariant measure, in which every ergodic invariant measure sitting in this copy of K is disjoint with this mu. I suspect that
it's almost one-to-one extension of the alpha rotation.
Yes, it is. But you get it by, say, there's a theorem by Dovnarovich and Yves Lacroix, and later a version of it was by Dovnarovich and Durand, and this is all based on Furstenberg and Weiss' work, which says basically that if you have a counter system which factors over your given minimal system, then you can realize it as almost one-to-one extension of this.
You realize also the simplex.
Yeah, but you keep this theorem of Dovnarovich and Lacroix give you that you can still do it keeping the simplex. So there are ways of basically.
You don't need something zero-dimensional as a factor, no? So you can take a rotation.
Well, in fact, I have the Sturmian of this as a factor also intermediate. So it's.
Okay. Yeah.
It is sitting there, but of course after collapsing I can recover the circle. So.
Okay. In that case, let's thank Dominik and everyone. And now we'll have a break and we start again at 2:30.
So should we like in 10 minutes? Have a lunch date?
So they know that they will get so there's a moral bijection.